All right, 8.4 bond energies. There were really two topics we talked about in this lesson. The first topic was bonds breaking and making, and the sign and the energy of that. And then number two, we talked about enthalpy, or delta H. Let's first talk about bonds breaking and making and the signs of that. There's two situations when you have bonds, right? You could break a bond, or you can make a bond. Bonds made. Students get confused by this a little bit, but let me make it clear for you here. If you break a bond, you're going to need energy. If you need energy, you're sucking it in from the surroundings. If you're sucking in, causing energy to enter in, that is endothermic, and endothermic reactions feel cold. Think about it this way, right? If I have this pencil, a pencil, right, is kind of like a bond, right? Like if you have two hydrogen atoms, right, they're held together by this bond, kind of like this pencil. If I want to break this pencil, I'm going to need to put in energy, right? You need to put in energy in order to break something, and that's what's happening when you break a bond. When you make a bond, conversely, you are going to release energy. Release energy is exiting, exo, that feels warm, right? Students get confused by this. They think that, if I eat food, then I break the food, and that gives me energy, right? And, they think similarly with ATP and everything. But that's not true, right? You're actually thinking about it the wrong way. This is the correct way. If you break a bond, you need energy. If you make a bond, you release energy. As always, you can think of chemistry and understand it better via relationships. If two friends are breaking up, feels bad, right? There's a lot of negative energy. If you walk into a room with a couple who's fighting, all the energy in the room is getting sucked in, and it just feels bad, and you feel bad, and not good. A lot of mental energy is being used up there, right? Whereas, if bonds are being made, right, people are like falling in love, relationships are moving forward, we love it, right? That feels good, right? Good vibes everywhere. They're giving off good energy. They're so happy, and you just feel good, right? And so think about it that way, right? Bonds are breaking, you need energy to do that. Whereas if bonds are being made, right, it's easy, good vibes, right? You release energy in that situation, okay? So know those two things. So that's the first concept we learned. The second concept we learned was this idea of enthalpy. Enthalpy is a big fancy word for the internal energy of a system. It's another way of thinking about it is just kind of the heat of a system. Now, it's not exactly heat, right? Because otherwise we'd call it Q. It's technically enthalpy delta H is equal to, I think, work plus QT, something like that. Where basically it's both work and heat. And then temperature has something to do there too. But just for this class, we're not going to really worry about work, and we're just going to think of H as Q. Okay, so it'll be more complicated one day, but so basically it's internal energy system, or basically the heat of a system. And so that's what delta H is. And so, when we're talking about the change in energy of a system, you might think, it's delta E, right? But no, actually we're going to use delta H, because chemistry, yeah. We love it. So now let's take a look at an example. If we were to take a look at C3H8 plus 5O2, making 3CO2 plus 4H2O, right? This is the equation for the burning of propane, right? This is propane. And so if you're burning propane, the question basically is asking, hey, what's the delta H of this? And is it endo or exo? The way we can do this is by using the two concepts that we just learned, bonds breaking and making, right? And the enthalpy, and this idea of a bond energy table. Basically, what we can do is we can draw out our molecules and then see how much energy it requires to break those bonds here, and then how much energy is released when we make new bonds here, and then we can tabulate those results and calculate delta H. And so here, we're going to draw out C3H8, which is C. It looks something like this, right? You have 3 C's surrounded by 8 H's. So it looks something like that. And then O2, it looks something like this. And so then what we're going to make is we're going to make CO2. We're going to make 3 of those. And then we're going to make 4 H2Os. Cool. So now, how much energy is going to be used in order to break these bonds, and how much energy is going to be released when we make these bonds? Well, what we're going to have to do is we're going to have to use this bond energy table. Basically, let's consider like this CH bond. This CH bond is going to, the average bond energy here is 413. So that means, right, we're going to break. So we're going to need 413 kilojoules of energy there to break that bond. And also this bond, and 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 this, right, because those are all CH bonds. We have, in total, 8 CH bonds. And so we're going to need 8 times 413 kilojoules of energy. If you put that in your calculator, you will get 8 times 413, 8 times 413 is equal to 3304 kJ. Right, but there's also other bonds here, right? There's also these CC bonds, and there's 2 of them. And so there's 2 CC bonds. Each of those CC bonds are 348 kilojoules. That's 2 times 348 kJs. So 2 times 348 is equal to 696 kJ. So that's another type of bond. And then the last type of bond is the O double bonds. So here, that's 495. And so we have 5 of them, 5 O bonds, 5 times 495 kJs. That equals to 2475 kJs. So now we can put it all together, right? Basically, we have 3304, 696, 2475. This is the total amount of energy used to break all of these bonds. You don't have to draw this, but basically, kind of like an intermediate step, right? It's like, okay, you're gonna break all these, and so now we're gonna have 8 hydrogens just kind of here, kind of like 8 Lego pieces of sorts that we can now use. And there's gonna be 3 carbons, and there's going to be 10 oxygens, right, from this. And so this is kind of like, you know, again, you don't have to draw it this intermediate step, but it's kind of like, okay, we just broke all these bonds, and so now we have this, so now we can make these. But to do that, right, we needed to use up this much energy, which is 3304 plus 696 plus 2475, and so you get 6475 kJ. Right, that's how much energy is needed to break the bonds, okay? And then here, what we're gonna do is we're gonna say, okay, well, how much energy is released, given out, negative, when we make these bonds? And so we see there is these bonds. These are when O is double bonded to C. That's O double bonded to C, so that's 799. 799. Now, one thing I did want to bring up here, I do note that O double bonded to C is different than O single bonded to C, right? So this is the single bond, this is the double bond, this is the triple bond. Okay, so don't fall for, and don't mix them up, right? Make sure that you use the right one for double versus single versus triple bond. But so yeah, here we have 799, right? And there's 6 of them. So 6 O-C double bonds, so that's 6 times 799 kJs. And so you get 6 times 799, that's 4794 kJs. And then here you have also these OH bonds. You have 1, 2, 3, 4, 8. Sorry, I was just double checking to make sure I didn't mess up that because I thought I put 8. But no, yes, 6 of these, 8 of these, 6 OH bonds. And so we have 8 times, what's the value here? OH, it's here, 463 kJ is equal to 8 times 463, just put it in my calculator, that's 3704. We add those together, 3704 plus 4794, you will get 8498 kJs. Do note that that's kJs released, so that's negative, right? So basically, in this first step, we take in 6475 kJs, and then here we release 8498 kJs. So what's our delta H? Well, our delta H for this whole reaction, right, is going to be the amount of energy that we take in plus the amount of energy that we lose. So it's going to be 6475 plus negative 8498, right? Sorry, these are both kJ. right? Technically, it's actually kJ per mole, right? And then what you'll get is you will get 6, 4, 5. You will get negative 2023 kJs per mole if you put that in your calculator, right? And so what we see is that this is negative delta H, and so overall, this is losing heat. It's losing energy, right? Because enthalpy is delta H. It's going to be losing heat, and so this is an exothermic process. Heat is exiting, it's leaving, we're losing it. And so that's how you would do this type of problem. Basically, draw it out, then use the bond energy table to get the bond energies, and then you can tabulate it here, calculate delta H, and figure out if it's endo or exo. And so I'm sorry, I should have also given you here the sign of delta H. Basically, the sign of delta H, right? If it's positive delta H, then that means that heat is entering the system. Heat slash energy is entering the system. And so that is going to be endothermic, right? Whereas if you have negative delta H, right, then heat slash energy is exiting the system. And we're going to say that that's exothermic, right? Exit, exo. And so that's going to be it's going to feel hot. And so that's the basic idea here. Hopefully that helped you guys out. Try out the practice problems, right? I make you guys a whole packet of them. I also give an example for you guys here. Try this out. Make sure that you know how to do them. You have your average bond energy table here, full examples. Practice makes perfect. This is really not a hard concept. It's a little bit annoying, I will say, right, to kind of tabulate all this. But it gives us really a basis for what it means for a reaction to be exo or endothermic, right? The question that I brought up at the beginning of this lesson for you guys, if you were in class, was why does fire feel hot? And it's basically because of this. And so fire feels hot because of the bonds being made. They release more energy than the energy we take in to break bonds. And so that's why it feels hot. So a little bit tedious, but not very hard. Okay, so give it a try, do some practice. Let me know if you have any questions.